Hi, I'm c.f.choudhury from University of Leeds. In my UKRI Future Leader Fellowship, I'm working on developing next generation activity and travel behavior models. And I'm doing it by combining choice modeling with data science and ubiquitous computing. In my team, I also have Dr. Thomas Hancock and Dr. Arash Kalatian, who are working as research fellows in this project. And they will also join in this presentation to provide updates about the interesting work we have done so far. So in terms of the motivation of this research, we know that transport investments cost billions, and they need good mathematical models to predict how users are going to choose different options when there's a new policy in place or a new mode like high-speed rail in place. So choice modelers like me, we work on developing mathematical models that establish relationships between the influencing factors like travel time and travel cost with the observed travel decisions. For example, what more people are choosing when they're choosing to travel, things like that. So one aspect of our work is we need to acknowledge the heterogeneity in the decision-making process of the users. So for example, like we know that the decisions vary depending on the age, gender, and income of the users, but there's also evidence that they depend on the mental states and the way people think, their attitudes and perceptions, things like that. So this brings us to the challenge that right now we are going through a lot of change in our mobility landscape. For example, there are new modes like Uber, shared bike. There are new concepts like mobility as a service. Then there are emerging technologies like self-driving cars, flying taxis, which are going to be available to the users in near future. On top of that, we also have a lot of heterogeneity among the users, which is actually increasing because of the globalization. So we have a user group who not only vary depending on the age, gender, and income level, but also who have kind of a difference in the thinking process. And in order to develop reliable models, we need to take into account this heterogeneity in greater detail. One recent example is during the COVID behavioral change over the last 1.5 years. We have seen that people have reacted very differently and changed their travel behavior very differently in response to the policies imposed on mobility, but also because of their difference in risk perceptions and stuff like that. So in this project, what we are trying to do basically is harnessing the power of big data sources, like passively generated data sources, like smart card data, mobile phone data, GPS data, etc. And also trying to combine choice modeling with techniques from machine learning models so that we can properly utilize these data sources. So that's one stream of the work. On another stream, we are trying to use virtual reality and ubiquitous computing so that we can immerse the travelers in hypothetical future scenarios and we get inference about their mental states from their physiological sensor data, like their skin conductance, their heart rate, even their EEG recordings, that what's happening in their brain when they're making decisions. And all these are going to be ultimately implemented in a simulation platform where they can be used to test the implication of different policy scenarios.
One of the topics that we have been exploring in this project is the potentials for the utilization of data science techniques in choice modeling. Traditionally, choice models have been theory-driven, meaning that the modeler makes assumptions about the decision maker based on behavioral theories. On the other hand, machine learning is based on a data-driven paradigm, meaning that the behavior of the users are learned through the data and not behavioral theories. Each of these two paradigms provide some opportunities and, of course, some disadvantages. The connection of choice models to behavioral theories makes their parameters easy to interpret and also easy to derive economic outputs from them. Also, they have a strong connection to stated preference surveys, which are the dominant way of data collection in choice modeling. On the other hand, machine learning models have shown to have better goodness of fit and easier model specification process, and especially they perform better on large and continuous streams of data. There are various possible directions to explore the ways that machine learning and choice models can help each other. Comparing the performance of the two approaches in different contexts can be one starting point, which can then lead to the integration of the two approaches. Connecting machine learning outputs to economic and behavioral theories can be another path to explore. Choice models can also be modified to use new and unconventional data sources, like images or text or videos. This is a case study that we have done on comparison of machine learning and choice models in the context of vehicle ownership. We used survey data from Bangladesh in 2010, and using that data, we developed two parallel models, as you can see in the figure. One of the models was using multinomial logit and nested logit model as choice models, and the other one was using neural networks and gradient boosting trees as machine learning methods. We wanted to compare the performance of the models in terms of their accuracy, their interpretability, and their transferability to the data from 2005. Using this study, we found that in our case study, machine learning could capture the non-linear relationships between variables better than the choice models. But on the other hand, choice models are still more suitable for policymaking due to their strong link to behavioral theories.
Another key aim of our project is to augment choice models with physiological sensor data. Physiological sensor data has been used extensively in marketing and psychology research, but as of yet has not made a significant step across to travel choice behavior modeling. Our idea is that by using physiological sensor data, such as eye tracking data, brain imaging data, or stress-related measurements, we can better understand how people perceive their alternatives, how they then process these alternatives, and how they ultimately make their choices. We have been developing a framework to include these factors in our choice models. And so far, we have done one case study where we've used this successfully. In this case study, we looked at a driving simulator data where we had participants navigating through a virtual world. In this virtual world, they completed a number of tasks, for example, crossing an intersection. When they crossed this intersection, there was a number of factors that might determine whether they choose to accept a gap and cross or not. So for example, the size of the gap or how fast these cars were going. But we also had information about where they were looking. So whether they were actually looking at the gap, looking forwards, or looking to the right here. And we also had information about how stressed they were, so they were wearing this wristwatch here. So by combining the physiological data with what we could observe, we could better predict the decisions that they made in this environment. If you're interested in our project and want to find out more details, or if you'd like to collaborate with us, we'd be more than delighted to hear from you. Please do get in contact with us. We also have a number of academic partners and industrial partners listed here. Thank you very much for listening.